You probably learned about the states of matter in school: solid, liquid, and gas. It's a simple, tidy list. You heat a solid, it melts into a liquid. You heat a liquid, it boils into a gas. It makes perfect sense. It's the world we see every day. An ice cube melts into a puddle of water. The puddle evaporates into the air. And maybe you learned about a fourth state, plasma. If you keep heating a gas, the atoms get so energized they start to fall apart. Electrons get ripped away from their atoms, leaving a hot soup of charged particles. This isn't something you see much on Earth, but it's actually the most common state of matter in the universe. The sun is plasma. All the stars are plasma. Lightning is a brief flash of plasma. So we have four: solid, liquid, gas, plasma. They are all linked by one thing: temperature. You start with a solid and you add energy, usually as heat. You go up the ladder from solid to liquid to gas to plasma. Each step represents more energy, more motion, more chaos in the atoms, but what happens if you go the other way? What if, instead of adding heat, you take it away? You take a gas and cool it. It becomes a liquid. You cool the liquid, it becomes a solid. The atoms get slower, more orderly, more locked in place. And then what? What happens if you keep going? What happens if you try to make something colder than any ice cube, colder than the deepest, darkest corner of space? This question leads us to a strange and wonderful place. It leads us to the fifth state of matter. To understand it, we have to change how we think about the world. Our everyday world is governed by what we call classical physics. If you throw a ball, you can predict its path. Everything is distinct. A ball is a ball. Another ball is another ball. They are separate objects. But when you get very, very cold and very, very small, the rules change. You enter the world of quantum mechanics, and in the quantum world, things are weird. One of the weirdest ideas is that everything, and I mean everything, isn't just a particle. It's also a wave. You are a wave. The chair you're sitting on is a wave. A baseball is a wave. You don't notice it because for big warm things, this wave nature is incredibly tiny. It's so small, it has no effect on anything, but for a single tiny atom, it matters. Each atom has a little wave associated with it. You can think of it like a fuzzy little cloud of probability, showing where the atom is likely to be. The key is this: as you cool an atom down, its wave gets bigger. Coldness, in physics, is just a lack of motion. When an atom is hot, it's zipping around, and its wave is small and tight. When you cool it down, it slows to a crawl, and its wave starts to spread out, getting longer and fuzzier. Now, imagine you have a box full of a certain type of atom. Let's call them bosons. Not all atoms are bosons, but many are. You start to cool this box of atoms down. Colder and colder. The atoms slow down, their little waves start to spread out, you get them colder still. The waves get even bigger. Eventually you reach a critical point. The temperature gets so incredibly low, so close to the absolute coldest anything can possibly be, that the waves of the individual atoms start to overlap. They touch, and then something amazing happens. They don't just bump into each other. They merge. All of a sudden, the thousands or millions of individual atoms in your box cease to exist as individuals. Their separate identities are gone. The boundaries between them dissolve. They all collapse into a single unified quantum wave. Or they become one entity. A single superatom. This is it. This is the fifth state of matter. It's called a Bose-Einstein condensate, or BEC for short. It's named after two people. Satyendra Nath Bose was an Indian physicist. In the early 1920s, he was working on the physics of light particles called photons. He came up with a new way to count them, a new way to do the statistics. He sent his paper to Albert Einstein. Einstein realized that Bose's math was a breakthrough, and he also realized it didn't just apply to light. It could also apply to certain kinds of atoms. Einstein took Bose's idea and ran with it. He predicted that if you could get a gas of these atoms cold enough, something bizarre would happen. He predicted that at some incredibly low temperature, all the atoms would suddenly drop into the lowest possible energy state. They would become, for all practical purposes, identical and indistinguishable. They would form a new state of matter. This was in 1924. It was an incredible prediction, but it was just a prediction. For the next 70 years, it was nothing more than a theoretical curiosity, a footnote in physics textbooks. Because making something that cold was considered pretty much impossible. How cold are we talking about? The temperature scale scientists use is Kelvin. 0 Kelvin is absolute zero. It's the point where all atomic motion is supposed to stop. is it's about minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. The coldest place in outer space, the deep void between galaxies, is about 3 Kelvin. That's cold. But to make a Bose-Einstein condensate, you need to get much, much colder. You need to be within a few billionths of a degree of absolute zero. That's not just cold. That's a level of coldness that doesn't exist anywhere in nature. It's colder than anything in the universe. The only way to reach such a temperature is to create it in a lab. And that took decades of brilliant, painstaking work. How do you do it? How do you make something that cold? You can't just stick it in a fancy refrigerator. The first problem is that you need a perfect vacuum. You have to get all the other air out of your chamber because a single stray air molecule bumping into your experiment would be like a meteorite strike. It would instantly heat everything up and ruin the whole thing. Once you have your vacuum, you put in a small cloud of the right kind of atoms. Those rubidium atoms were used in the first successful experiment. Then, the cooling begins. It's a multi-stage process, and each stage is a clever piece of physics. The first stage is called laser cooling. This sounds completely wrong. Lasers are supposed to be hot. They cut through steel. How can a laser make something colder? It works because of a neat trick. You set up 6 laser beams, one pointing in from every direction, up, down, left, right, front, back. These lasers are tuned to a very specific frequency. They are tuned so that they are slightly below the frequency that the atoms naturally absorb. Now think about an atom moving towards one of the laser beams. Because moving towards the light source, the Doppler effect comes into play. It's the same reason an ambulance siren sounds higher pitched as it comes towards you and lower as it goes away. For the atom moving towards the laser, the light's frequency appears to be shifted up, right into the sweet spot where the atom can absorb it. So the atom absorbs a photon from the laser. When it absorbs the photon, it gets a tiny kick backwards, slowing it down. It's like the atom is running into a headwind of light. A moment later, the atom spits the photon back out in some random direction. The kick from spitting it out is random, but the kick from absorbing it is always directly against its motion. Over and over, millions of times a second, the atoms are hit by photons that slow them down. Since temperature is just a measure of motion, slowing the atoms down is the same as making them colder. This process of laser cooling can get the cloud of atoms down to a few millionths of a degree above absolute zero. That is astonishingly cold, but it's still not cold enough to form a Bose-Einstein condensate. To get the rest of the way, scientists had to use another trick. After the laser cooling, the atoms are still moving, just very slowly. So the next step is to trap them. You can't put them in a physical box because they would touch the walls and warm up. Instead, you use a magnetic trap. A carefully shaped magnetic field acts like an invisible bowl, holding the cloud of slow-moving atoms in the middle of the vacuum chamber. Now comes the final, crucial step. It's called evaporative cooling. It's the same principle that cools you down when you sweat or that cools down a cup of hot coffee. The hottest, most energetic particles are the ones that escape as steam, leaving the cooler ones behind. This lowers the average temperature of the coffee. In the magnetic trap, the scientists do the same thing with the atoms. They slowly lower the size of their magnetic bowl. This allows the most energetic atoms, the ones with enough speed to make it over the rim, to fly out of the trap and be sucked away by the vacuum pumps. The atoms that are left behind are the slower, colder ones. As the hot ones leave, the average temperature of the remaining cloud drops. The scientists keep lowering the walls of the trap, letting more and more of the host's atoms escape, until the atoms left are unbelievably, unimaginably cold. In 1995, at a lab in Boulder, Colorado, a team led by Eric Cornell and Carl Wieman did it. They took a cloud of about 2,000 rubidium atoms. They cooled them with lasers. They held them in a magnetic trap. They used evaporative cooling to get them colder and colder. And then they saw it. They had a special camera that could measure the speeds of the atoms in the cloud. At first, they saw what you'd expect. A bell curve. Some atoms were a little faster, some a little slower, but most were clustered around an average speed. This is just normal thermodynamics. But as they crossed that final temperature threshold, a new peak suddenly appeared on their graph. It was a sharp, impossibly narrow spike right at zero velocity. It was like a huge chunk of the atoms had suddenly stopped moving altogether and piled up at the exact same energy state. The bell curve of individual atoms was still there, but rising out of it was this new feature, representing a new form of matter. They had done it. 70 years after it was predicted, they had created a Bose-Einstein condensate. They had created the fifth state of matter. For this work, Cornell and Wieman, along with Wolfgang Ketterle, who achieved it independently a few months later, won the Nobel Prize in Physics. So what is this stuff? What is a beak really like? It's a very strange thing. It's a gas, but it acts with a single coordinated identity. It's a quantum phenomenon that is big enough to see. Normally, quantum effects are confined to the subatomic world, but a BEC can contain millions of atoms and be large enough to see with a microscope. It's a bridge between the tiny quantum world and our large-scale classical world. In a BEC, all the atoms are in lockstep. They don't act like individual particles anymore. They act like one single object. This leads to some truly bizarre behaviors. For example, a BEC can be a superfluid. This means it can flow without any viscosity, without any friction at all. If you were to stir a cup of superfluid, it would literally never stop spinning. It would spin forever. You could pour it through a crack so small that a normal liquid couldn't get through. The BEC would flow through it without any resistance. This coordinated behavior is because all the atoms are part of the same quantum wave. Think about dropping two pebbles into a pond. You get two sets of ripples that interfere with each other, creating a complex pattern. Now imagine you could split it back in two, move the two halves apart, and then bring them back together. Because they are both parts of the same original quantum wave, when they recombine, they create an interference pattern, just like the ripples in the pond. But this is an interference pattern made of matter, not just water. It's a direct, visible demonstration that matter has a wave nature. This all might sound very abstract, a weird form of matter that only exists in a few specialized labs around the world for fractions of a second. So what's the point? Why spend so much time and money creating something so fragile and exotic? One of the biggest reasons is that a BEK is a perfect laboratory for studying the quantum world. Quantum mechanics is famously weird and counterintuitive. It's hard to get a handle on it. But with a BEC, you can see quantum effects in action on a macroscopic scale. You can poke it, shine light on it, stir it up, and see how this giant quantum object responds. It allows scientists to test the fundamental theories of physics in a new and controllable way. It's like having a magnifying glass for the quantum realm. The properties of Beck's are also helping us understand other important phenomena, like superconductivity. A superconductor is a material that can conduct electricity with zero resistance. Imagine power lines that never lose energy, or super powerful magnets for MRI machines. Superconductivity is a quantum effect closely related to the physics of a BEC. By studying BECs, we can learn more about how to create and control superconductors, hopefully leading to new technologies. There are also more direct applications being developed. One of the most exciting is the atom laser. A regular laser produces a coherent beam of light. That means all the photons are in step with each other, marching along with the same frequency and phase. An atom laser does the same thing, but with atoms. Using a Bose-Einstein condensate, scientists can create a coherent beam of atoms that can be controlled and directed with incredible precision. What could you do with an atom laser? You could use it for incredibly precise measurements. Because atoms have mass, they are sensitive to gravity. A beam of atoms could be used to make devices that measure tiny changes in the Earth's gravitational field, which could be useful for finding underground oil deposits or monitoring volcanoes. You could also use them to build atomic clocks that are so accurate they wouldn't lose a single second in the entire age of the universe. Atom lasers could also be used for atom lithography. This means using a beam of atoms to write incredibly small circuits onto a silicon chip. Because the wavelength of a cold atom is much smaller than the wavelength of light, an atom laser could potentially create computer chips that are far smaller and more powerful than anything we have today. And in the long run, understanding how to manipulate these collective quantum states is a crucial step towards building a quantum computer. A quantum computer would be a revolutionary device that could solve problems that are impossible for even the most powerful supercomputers today. Building one requires controlling the delicate quantum states of many particles at once. A BEC is a system where millions of particles are already acting as one quantum state. It's a natural starting point for exploring these complex challenges. It's strange to think about. We live our lives surrounded by solids, liquids, and gases. We look up at the sun and see plasma. These four states define our world. They are built on the idea of individual atoms and molecules bouncing around, sticking together, or flying free. They are noisy, messy, and chaotic. The fifth state of matter is something else entirely. It is a state of profound quiet and order. It is a state where the clamor of the individual is silenced, and a single, unified quantum identity emerges. It doesn't happen in the heat of a star or in the everyday jumble of our world. It happens only in the deepest, most profound cold we can create, in a place where the ordinary rules of physics give way to the strange and beautiful logic of the quantum. It's a reminder that even the most basic concepts, like what it means to be a solid or a liquid, are just part of a much bigger and more mysterious picture. The universe is always more complicated and more interesting than we think. And by pushing the limits of what we can do, by reaching for the absolute coldest temperatures possible, we found a whole new way for matter to be.